Well, thanks in particular to the organizers for having me here, which is quite wonderful, even when the weather is not great. So I feel very fortunate. I'm going to talk today about quantum spin liquid. So it's not very related to much of what has been talked about, although I'll make some connections. There's some connections, of course. So the way I'm going to be giving 2 lectures, and first I'll be talking about general aspects. So kind of giving you some, in fact, phenomenological point of view, leaving aside a very mathematical approach, which is also very interesting. But I'm not going to do any classification, any very formal statements of any kind. I'm just going to try to give you a little bit of the physics and the phenomenology. And hopefully today I can already start with some models and materials because I believe it helps in fact understanding what might seem a little bit abstract. And here's a reference. There are others, but at least I know what's in this one, so it's a good start. So the first question, talk about quantum spin liquids, is what are they and why should we be interested? So what I want to start by saying is that there are states of magnetic insulators. So here there are no electrons. I mean, you could imagine eventually cooking up something where you also include or couple your quantum spin liquid to electrons, but it's not necessary. And in fact, the basic idea is that you have insulators. So perhaps, you started with a Hubbard model and you tuned U to be very large and got into a to a mod insulator. Such that the gap to any delocalized electronic degrees of freedom was very large. So you can forget about the electrons entirely. And again, rather than giving a very precise definition, which in fact I'm not sure really exists if we want to be fairly general, is I want to say they're essentially the most quantum states of magnets. And that's in the sense that they are quantum superpositions of very many product states. So product states are essentially more or less classical states, and these not only are quantum spin liquids a quantum superposition of very many product states, the superposition cannot be adiabatically deformed to a product state. Okay, so the best is to start with pictures. So a classical state, which is typically the state of magnets that everyone will have seen, even if you don't work on magnets in a statistical physics class, is a state where you have spins that can be described as arrows and they point in some direction. Okay, and this is a very simple case where all the spins are aligned, but you could have a lot more complicated and in fact very interesting states where you might have skyrmions, antiferromagnets, all sorts of interesting things. And so that's a classical state, and a product state, so the quantum version of a classical state, would be basically the same thing. So physically the same thing. Perhaps, the magnitude of the spin because of quantum fluctuations would be slightly reduced if you were to measure its expectation value. So that's not a quantum spin liquid, clearly. And even if you had a ground state where you had spins that were entangled, but entangled locally, that would still be a product state where your blocks would be bigger than single sites, but they would still be, you could still describe them as a product state, and this would also not be a quantum spin liquid. So a quantum spin liquid, the picture would be something more like this, where at no point, even if you kind of smoothly deform the wave function, you're not going to be able to deform this guy into different blocks, because there's going to be, we're going to talk about entanglement a little bit later, is going to be entanglement which is going to connect different blocks, and you can't get rid of that entanglement. And despite the properties which make quantum spin liquids interesting, as I will return in a second, despite the fact that the emergent properties are non-local, the Hamiltonian is perfectly local. Okay, so it's a perfectly legitimate Hamiltonian in a material. It might be a nearest neighbor Heisenberg model, for all we know. Of course, not on the square lattice. Okay, we know that the ground state of the Heisenberg model on the square lattice is simple. But for example, on the Kagome lattice, there are indications that the Heisenberg model may give rise to a quantum spin liquid. Okay, so you might need some frustration, but regardless, nearest neighbor interactions could perfectly well do the job. It's only the emergent properties that are non-local. Okay, so I haven't come yet to, I've sort of mentioned what quantum spin liquids were, but I haven't said why they're interested. I mean, why would you be interested in such a state? Perhaps it's fundamentally interesting, but okay, what can you say more about the physical phenomena that emerge from these large quantum superpositions? And really, probably one of the main interesting aspects of quantum spin liquids is that they are emergent gauge fields. And you've all heard about gauge fields, of course, and in particular in the context of electromagnetism. And in fact, there exist quantum spin liquids which are basically emergent electromagnetism on the spin system. Okay? But there can be other types of gauge fields. It's not just U1, typically the ones that are often studied, or Z2, etc. But you could also imagine having non-abelian gauge groups. Okay. So, and these gauge fields, in fact, are the fields that mediate some interactions between the fractional particles, which are particles which emerge out of this entanglement. And when I say particles, really, I'm thinking about excitations above the ground states as described by particles. And this is kind of an assumption that we make, although in most cases of interest, this can be kind of proven to be true. So a particle is something which has, a definite momentum, perhaps a definite, at least if you're in a translationally invariant system, perhaps a definite charge or a definite quantum number if you have symmetries. But as I will insist later, symmetries are absolutely not crucial for quantum spin liquids. So what are fractional particles? I guess we heard a little bit about this in Charlie's talk, although here the fractional particles are really going to be mobile excitations in the bulk of your system. And they're not going to be confined to the edges of your system. Okay? So what's an integer particle to begin with? If I'm thinking about excitations, right, what can I do if I had an electronic system? Well, in an electronic system, I could add or remove an electron. And that particle, that excitation, would then have charge minus e if it was an electron, and spin 1/2. Okay, so those are the kind of the particles that we may get from. Can think about them as particles from our, the high energy table of particles. Okay. If you think about spin flips, so you just have spins. Now you don't have electrons. If you think about spins, well, your ground states, so just even if you just have one spin, and the Hamiltonian that conserves as C, you could think about a state which is pointing down, so as Z equals minus 1/2. And okay, you're going to say this is fractional, but really we don't care about the ground state. We want to ask about the quantum number of the excitation. And the excitation in this case actually has as Z equals 1 and charge 0. And that's another integer particle which you can construct out of a finite number of elements. Okay. So a fractional particle would be, for example, a fraction of any of these things. So it could be, for example, a particle which charge 0 like this, but then spin half like this, but none of the two are the same. Okay. And again, here I'm talking about quantum numbers, which are not strictly necessary for quantum spin liquids, but it's quite convenient to understand what we mean by fractionalization. So why does fractionalization require large superpositions? And another way to say this is some entanglement. Well, so imagine that, again, we're considering the eigenstates of total spin. perhaps our Hamiltonian conserves total spin. And we're thinking about one particle or one site or one qubit, and we go from spin down to spin up. So this is a delta SZ equals 1 excitation, and really you can't see how you're going to make a fractional excitation out of this single particle. Okay, the only thing you can really do is just flip the spin, and the excitation is going to belong to this spin 1 representation. Now, if you could say, well, okay, let me try with 2 particles. So with 2 particles, of course, it's a little bit more complicated. Nevertheless, we know that the excitations for an eigenstate of total spin, if the spin is a good quantum number, that it's still going to be basically additions of spin 1, okay? And you could keep playing that game forever, but you're not going to be able to create these fractional particles out of a finite number of constituents, at least in dimensions more than 1. I'll say that in a second, okay? So this was kind of a cartoon picture to try and convince you that you needed a large superposition. This is an aside because sometimes it's a little bit confusing. This is actually not strictly true in 1D that you need a large superposition to make these fractional particles. And this is, if you just take the example of the Ising model on the spin 1 chain, you know that one of the ground states, or it's even just a classical ground state, right? Because this is a classical Hamiltonian where all the operators commute with one another. Is all spins, aligned along one direction. It could be this one, or it could be the other one. Okay, and if you were to flip a spin, that would be an excitation which costs energy 2J. Okay, but if you now were to flip other spins away from the first spin that you flipped, the cost of the excitations is no more than it was to begin with. Okay. Yeah, in fact, I guess it's 4J. Anyway, it doesn't matter. The point is that it's so here it should be 4 and 4. The point is that when you the energy of this state is no lower than the energy of this state, and in fact, this has been seen, for example, by Bella in this compound, which is a 1D compound. And the fact that you have this this diffuse scattering here is associated with the fact that you have 2 kind of independent domain walls. Okay, and I'll return to this, but probably in the second part of my lectures. Okay. So I guess this is kind of a summary on this bigger slide of what I just said 2 slides ago. Which is that for if you have a non-quantum spin liquid, so product state like, all excitations can be deduced from each block, and each block being finite has a finite number of excitations which you could do in each block. Okay, and this is different from a quantum spin liquid. So what kind of state is this? Okay. And I'll just first give a little bit of a historical slide, although it's not the most, perhaps not the most explicit example, but it's the historical example, and it has the advantage of showing you a singlet, so kind of products of states, kind of like in this form, which is a little more complicated than this guy's. So the idea of quantum spin liquids really came from Anderson, who was wondering about ground state of spin half systems. I'm giving a short version here, and the idea, the states that he defined were so-called resonating valence bonds. So what are these states? So one way to think about this is also because of the historical development on quantum spin liquids, which were usually defined by what they are not and not by what they are. So I try to give a bit of a definition of what they are. Historically, and that's because of kind of this development, spin liquids were defined as states which didn't break any symmetry, okay? Neither a translational nor spin. And if you have a valence bond solid and you take each pair of states, each pair of spins in a singlet, you haven't broken neither spin rotation or time reversal symmetry, etc. Okay, but you have broken translational symmetry. Okay, so what a valence bond solid is a single realization of putting singlets. So basically covering here your triangular lattice with singlets. Okay, so you take these pairs; these two pairs form a singlet. Okay. And now I want to ask, again, I'm thinking about excitations again. As I mentioned, this is what we're most excited about for spin liquids. And if you imagine that you break this singlet here and you turn it into just two spins up, and you want to say, well, okay, if I made this excitation locally, if I were able to separate these two spins, then each one would be a fractional particle. Each one would be a fractional particle. However, if I try to do this, then what you see happens if I'm moving this guy, around, I'm disturbing the state. So if this is supposed to be a ground state of my Hamiltonian, now I see that by moving the spin around, I leave this kind of trace of this line of valence bonds here that are very different from the arrangement that was in what we know is the spin liquid. Okay, and it's this guy, only locally disturbed it, but now this guy is actually creating a line of what we will call defects. And if you move these two things away to infinity, you would actually get an energy cost which would a priori be scaling like the length of the distance between the two spins that you've taken apart. So what this resonating valence bond is, and it's an example of a quantum spin liquid, is basically a quantum superposition with perhaps different prefactors here, but this is a detail of all these different possible valence bond solids that you could form, leaving a trace behind by separating two spins like I'm doing here. And the reason, and so the point is that now these two particles can be considered to be free of one another, because if you move them, if you separate them along this path, then you get a state here which is already in the superposition. And so what you've just done is by separating particles away and leaving traces of these separations of the spins with one another, you're just creating a reshuffling of the terms in your superposition. And so this is the notion that the quasi-particles are deconfined because pulling them apart, creating these strings doesn't cost very much energy. Okay. So now we can make a little bit of a statement, and so this is an entangled state, especially if you want these particles to be deconfined wherever you take them in your system. Okay. I don't know why it's. Well, so there was water actually in this thing. It was dipping in there, but it seemed to work. So I don't know. Or maybe it's this. When I press this, it seems to. Okay. Even though it's not like.
Do you have any other possibility of connecting? Okay.
Maybe it's okay. Let me try with this. Okay, so so perhaps I can also give a little bit of a more precise statement about entanglement. what is entanglement? So we can see it in pictures. You have quantum superpositions of product states, etc. They're very large. But there's been definitions of measures of entanglement, okay, of quantum entanglement. And in fact, there's lots of different measures of this, which are more appropriate in some circumstances and less in others. The entanglement entropy S is particularly useful when you have topologically ordered states, but because you can have a universal topological entanglement entropy in that case. But I'm not going to really go into detail about with this. I just want to say that this is kind of one of the ways that in numerical experiments, the entanglement entropy, the system may be deemed to be a quantum spin liquid. And so this is the von Neumann entropy, and what it tells you, what it does is it tells you how much a subsystem A, which you should be able to choose freely, is entangled with the rest of your system. So it involves the density matrices, etc. Quantum spin liquids have some specific scaling of the entanglement entropy of a subsystem A embedded in a subsystem B. Okay, and again, it's a bit there's lots of works on this, and it's a bit well, okay. As you'll see in a second, it's not. It's mostly particularly useful when your quantum spin liquid is a topologically non-trivial state, a topologically ordered state. So I was mentioning, that you have these that the quantum spin liquids require large superposition. So something which looks like long-range entanglement of different parts of your system. So, in fact, quantum mechanics indeed allows volume law entanglement scaling of your entanglement entropy. That is, that the entanglement entropy of your subsystem A scales like the volume of the size of your subsystem A. Okay, and these states actually exist, but they are very rarely, if not never, actually ground states of your system. They're more like excited or random states in your system. So both ordered and quantum spin liquid states have what is called area law entanglement, which means that the subsystem A has an entanglement which scales like the boundary of subsystem A. And if you think about the valence bond solid and you were to make, a subsystem A that went and intersected bonds, then indeed you could see that this entanglement is not actually volume law, but it's local because each spin is entangled with its neighbor. Okay. But what is particularly interesting about entanglement entropy for quantum spin liquids is that there is actually for not general quantum spin liquids, topologically ordered spin liquids, is that there is a part here which is related to the quantum dimension, which Adam talked about, which is universal, and that doesn't depend on the details of the system, whereas the proportionality constant here for ordered or quantum, of the area law actually depends on the details of your system. But the outcome of this is that because the ground states of spin systems, of gapped spin systems, not gapless spin systems, because they satisfied the area law entanglement, there's very good numerics, such as the MRG, can be very good at detecting them and can be applied because these things are kind of tailored for area law entanglement versus volume law. Okay. So let me mention a few points. I want to insist that quantum spin liquids are not degenerate states. So a valence bond solid in a system whose ground state is a degenerate state, is a degenerate set of valence bond solids, is not a quantum spin liquid. You need a superposition. So for those of you who know classical spin ice, it's not a quantum spin liquid. Okay, and we'll see this in a second. So it's not the degeneracy. The degeneracy can help if you add quantum fluctuations to your degenerate manifold, but it's not a quantum spin liquid itself. Moreover, they are very stable states. Okay, so if you have a quantum spin liquid and you know there exists a quantum spin liquid at a given point, you can add perturbations. So if you know how to solve your problem at a given point and you add perturbations away from this, you're going to stay in a quantum spin liquid phase. And presumably you'll need a phase transition. And this you should actually be fairly familiar with, because we know some of the quantum spin liquids are topologically ordered, and we know that to exit a topological phase, to go to a trivial phase or another topological phase, you need a phase transition. Then again, they're obtained from local interactions. Okay, so even though the characteristic properties are non-local, they're obtained from local interactions. And something particularly important is because these emergent particles, so think about these spins I took away from one another, are non-local, and the probes we have in condensed matter are typically local. They're actually very difficult to find experimentally. Not only to find, but also to probe. And finally, you might be wondering why I haven't told you how to find a spin liquid. Well, the point is there's no single sharp indicator of a quantum spin liquid. So there's each smoking gun, as we will see in the examples, each smoking gun signature is actually a function of the spin liquid you're looking at. So let me also now turn to actually a theorist's tool. Okay, so how are we going to, as a theorist, describe, understand the physics of a spin liquid? Well, you know that, for usual spin models, okay, a spin model always will typically look like this. You have an exchange interactions between two spins. That's the most common one, usually the largest term. And then you may have a magnetic field, which couples with possibly a G-tensor to the spins. Okay. And here you'll notice I didn't just write the Heisenberg interaction because the interactions could be totally anisotropic. Again, because there are no symmetry requirements for a quantum spin liquid. Okay. They can be enriched by symmetries, but you don't need symmetries to get a spin liquid. And so what you typically do when you have a model like this is you do what you know how to do, which is mean field theory. And so you write the mean field Hamiltonian by taking the expectation value of one spin, leaving the other one free. And then you get a mean field Hamiltonian, which you may rewrite just as a spin in an effective field. Okay, the effective field being given by this. And then you have to solve self-consistently. And this may be a hard problem, but in principle you can obtain a phase diagram, transition lines, etc. And what's going to distinguish your ordered phase from your paramagnetic phase, according to Landau's theory of phase transitions and of phases, is that the expectation value, if you solve this self-consistent equation and find that the expectation value of the spin is non-zero, then you are in the ordered phase. And if you solve this and find that the expectation value is zero, then you're in the paramagnet, and that distinguishes your phases. Okay, but because our states, they're quantum superpositions, right? So this guy, in fact, in the original historical definition of spin liquids, if you think about the resonating valence bond state, for example, this is just going to be zero. So if you start proceeding with Curie-Weiss or with mean field theory to solve your Hamiltonian, you're not going to get anywhere, because you can certainly carry out this thing, but a zero expectation value might not tell you any information about the actual state of your system. Okay, and you can see the reason is that here it's a characteristic in this mean field theories, it's a characteristic of one site, or perhaps a few sites, okay? But we said that what was really important was actually that there was something long range. So anything that tells you about a single site is not going to give you any information about your spin liquid. So what are the tools we can use? I mentioned that one of the most fundamental properties of spin liquids, or one of the interesting properties of spin liquids, was that there were emergent particles and emergent gauge fields. And so there is this procedure which is usually undertaken, which is a parton procedure, which is an attempt to postulate the right quasi-particles. So if I know that, say I should have quasi-particles that emerge that should be bosons, then maybe, description of spins in terms of Schwinger bosons will be a good description, because from a spin, I can have a spin operator at a single site creates two bosons. So it sounds like this could be a pretty good starting point. If I think that my fractional excitations are fermions, then perhaps an Abrikosa fermion rewriting could be a good one. There are others. This is also a boson rewriting, where these guys are more like angular momentum creation and annihilation operators. And so this resembles more electromagnetism, where, say, if you flip a spin, you create a particle, an antiparticle, and you have a gauge field in between. Okay, or it could be Majoranas. You can also, so Kitaev showed us that you could also rewrite spins in terms of these Majorana decompositions. And you have to bear in mind that if you rewrite the spins like this and impose these constraints, which restrict the Hilbert space of your bosons, fermions, rotors, or Majoranas to have the same number and the same commutation, the right commutation relations for the spins, this is an exact decomposition. So you could do this. In fact, you could do all of them, or maybe all of them at once. Okay, it might not be a good idea, but you could. Okay, and this is going to be exact. You're not going to lose any information so long as you impose these constraints. Only these constraints are actually very hard to solve. Okay, and so in fact, for the system to be tractable, typically these are treated in mean field or treated in some approximation. Okay. So this is kind of a statement. So even though we start, so first of all, one has to postulate what the right decomposition is going to be, and that depends on your physical system. Say if you want bosons or fermions, etc. But also you have to impose these constraints, and up to the point where you're treating these constraints approximately, then this is a perfectly exact description. Another thing I want to mention about the constraints related to my comment about gauge theories is that these are all local constraints, and local constraints which commute with the Hamiltonian. And in fact, these local constraints, this local freedom, is exactly a gauge theory. Okay, so there is a gauge. The fact that there is a constraint is associated with the fact that there is an emergent gauge field if you take these descriptions. And we'll see this more explicitly on these other examples. Okay, so are there any questions? Perhaps is a good time. No? Okay. So for gauge theory, I can give the example of electrodynamics, which we all know. So we have Maxwell's equations, which can be seen as constraints, kind of like this, on the E and B field. Okay, and we know that if we introduce a scalar and vector potential, we solve some of the constraints. But there is still some freedom. So we know that without matter, the theory is invariant under this shift here. And what we know also is that, I mean, another way to see, electrons and holes and electromagnetism is that the positron and the electrons, okay, they're defects of the gauge theory. So they're places where the theory without matter is the constraint for the theory without matter. So if we, for example, put divergence of E equals 0 here, is not satisfied. But these particles, the electron and hole, they can be created out of the vacuum, and they exist on their own. We know that electrons, despite the fact that they're described by, they interact with other electrons and positrons with gauge fields, they exist on their own. They've been seen, etc. So they're good particles. Okay, and we can create them from a local operator, except every time we create them, we create two of them. So we create a pair. You can't just create a single electron out of the vacuum. And as they move away from one another, you start developing field lines. Okay, this is just really electrodynamics from undergrad. Okay, and in fact, this is more or less the picture of a quantum spin liquid. Of how the quasi-particles that emerge in a quantum spin liquid look like. Okay, so you have the gauge fields, which come from these constraints that you defined here if you're a theorist. And then you have these quasi-particles which are almost free. They're only constrained by the existence of the field lines that must emerge out of the particles. So there are different types of quantum spin liquids, and in particular, there are different types which depend on the gauge field. Okay, so on the constraint that if you're a theorist, you've chosen. If you're a nature, you've also chosen, but you've chosen right. Okay, so they're also distinguished by whether they're gap or gapless. Perhaps they're distinguished by whether or not they have fractional particle statistics, as we've heard about from Adam Stokes. And all of this is kind of independent of whether or not we have symmetries in our system. But you can ask about symmetries, and this is called enrichment. And then you can classify the quantum spin liquid further, for example, with how each quasi-particle which emerges transforms, okay, under these symmetries. But this is not crucial. And so here are a couple examples. So we have the Z2, for example, the toric code. And other, topologically ordered quantum spin liquids which have gapped matter. We have examples of Coulombic spin liquids, which I'll discuss in a second, which is emergent electrodynamics, which also has gap matter, but is actually gapless because there is an emergent photon mode. And then we have other types of spin liquids, which are usually obtained theoretically using Abrikosov's rewriting, and they're fermionic with gapless matter, which may be, Dirac cone or an actual Fermi surface for these particles. And the Kitaev honeycomb model is an example of a Dirac. Of a spin liquid which has Dirac dispersing Majorana fermion in its bulk. Okay, and another version of this, which we'll also discuss, which is really topologically ordered and which have edge states of Majorana fermions, which correspond to the Ising-Aignan phase, which was also discussed by Adam. Okay. And there are many more types when you consider symmetries. And again, I'm not going to go into the classification. Some subsets have been classified if you put constraints. Okay. So let me go to describe what quantum spin-ice is, and hopefully this will make things, yes.
Is it any quantum spin liquid topological order?
No.
No, okay.
So topologically ordered states, at least I don't want to be too general, but there is a number of topologically ordered states which are quantum spin liquids. But this one, for example, is not a topologically ordered state. Okay. In fact, it's gapless. It's 3D. So
one more. The future then of having anyons means
that's only anyons would be only. I mean, when you can define them. So you'd have to be in a topologically ordered phase. You'd have to be in 2D, etc. So you have, I'd say, you have partons, but they're not necessarily anyons.
So having anyons doesn't imply you are in a quantum spin liquid?
I'm not sure I can make this statement because I'm not in the this kind of more mathematical business. But there are a number of topologically ordered states which are quantum spin liquids. Then perhaps you can cook up other topologically ordered states which are not. I mean, I guess the fractional quantum Hall effect is a topologically ordered state. Some fractional quantum Hall states are topologically ordered, I guess. But that's not a quantum spin liquid. I mean, yeah.
Okay, thanks.
Sure. Okay, so quantum spin-ice is actually stable. It's a quantum spin liquid, yet it's not topologically ordered. The reason I'm presenting this, which is which is perhaps not super common, is that there's a very physical and good picture. Then you can really go back home with a picture of what these fractional excitations might be. Okay. So another good point about quantum spin-ice is that there's actually candidate materials. So the Hamiltonian is a bilinear in spins. Okay, so it's not like the Tor code, which in its simplest version involves products of more operators, and so might be harder to realize, at least in a simple form, in a real material. But quantum spin-ice is not like this. So the Hamiltonian, it looks complicated here, but in fact the minimal terms here that you need are the Ising term with antiferromagnetic coupling, so positive J, and then quantum fluctuations, which can have any sign. So basically, it's an XXZ, so the minimal model, which gives you a quantum spin liquid, and which we'll be able to solve, is an XXZ model on a Pyrochlore lattice. So what's the Pyrochlore lattice? It's a lattice of corner-sharing tetrahedra, so it's three-dimensional. And you can see that you have units, basically, because it's corner-sharing. You have units which are tetrahedra here, and they'll become important, which are only one site with the neighbor unit. Okay, and the spins that I've written here, okay, they are expressed in the local bases. So for the local, the z-axis here is actually the axis which connects the centers of the tetrahedra. And the reason that this is important is for if you want to, actually apply this model to be a good Hamiltonian, a symmetry-allowed Hamiltonian in materials that have essentially cubic symmetry. But if you don't want to worry about this looks too complicated, okay, the local axes, you can't figure out where they are. In fact, once you've written down this model, you can just consider that these interactions are just all global. So you can think about your z-axis as being a local z-axis. Okay. In reality, because you need spin-orbit coupling to get a non-Heisenberg model, it is necessary to think about local axes, but if you don't want to think about this, now that I've given you the Hamiltonian, you can forget about it. Okay. What's important though is that we're dealing with these tetrahedra. Okay. And so the first term here, is the so-called classical spin-ice model. And so it's classical, you have only SZ as the operators, so they all commute with one another. Okay. So there's no way that from this guy, for example, you're going to get a quantum spin liquid, because there's nothing that wants you to make superpositions in this case. Okay. So that's why, well, it's not why, but the second term, if you're going to have just two terms, you need to have another term which includes quantum fluctuation, so non-commuting terms. Okay. And this model, in fact, in some parameter regimes, has in its phase diagram U1 Coulombic quantum liquid. So it's emergent electrodynamics on the lattice, and it exists only in 3D because these kinds of theories are only stable in 3D. Because these are results from gauge theories, studies of gauge theories. Okay, so let me go back to the minimal model, so drop these terms. So basically these terms will describe more or less any material which lives on the Power-Clear lattice. They're only constrained by symmetry, but I'm going to restrict myself to the first two terms for now, because they're the minimal ingredients. So let me first, in fact, focus on the first term, classical spin-ice, and turns out we can solve it. And the way that one can solve this Hamiltonian, i.e. find the ground states, and in fact also the excited states of it, is by rewriting this bilinear term as a square of sum of just single spins. Okay, so if you expand, so now T is a tetrahedron, so like this guy. Okay, and if you expand the square here, and you have a half factor, you recovered this guy. Only this expression is very nice to solve the Hamiltonian, because it is a square and this guy is positive here. You know that in order to get the minimum state, what you need to do is you need this thing to be equal to 0. Only each SZ is plus or minus 1/2, which means that in order to make 0 out of plus or minus 1, or plus or minus 1/2, you need to have two spins that are up and two spins that are down. And it could be any. It could be 0 and 1 which are up, and 2 and 3 which are down, or 0 and 2 which are up, and 1 and 3 which are down, etc. And this is actually doing choose 2 choose 4, which is equals to 6, which means there are 6 different possibilities which on each tetrahedron will satisfy this minimization constraint. Okay, and those are called so they're the 2 up, 2 down, or 2 in, 2 out. It means the same thing. And what happens is, because you have this degeneracy, the sixfold degeneracy on each tetrahedron, and the lattice is covered by tetrahedra like this, you actually end up with an extensive degeneracy. So because each tetrahedron is almost independent, so the choice that you make for each tetrahedron here is almost independent of all of its neighbors. So there's a correction because they're not entirely independent, but they're more or less independent, so that you have this extensive degeneracy. Okay, so this you have an entropy which grows like the system size. Okay. And classical spin-ice is basically the choice of one of these possible spin-ice states, or thermally a choice of the system might thermally go from one state to another if you're at non-zero temperature. Okay. And already in this case, one can think about fractionalization. It's not going to be really full-fledged quantum electrodynamics, but rather electrostatics or magnetostatics. But there's a very good picture of what this fractionalization and so what these fractional particles are. So here I've drawn two tetrahedra, so one tetrahedron at R and the other at R prime. And I've drawn this tetrahedron with two spins, two blue spins and two red spins. So two spins up and two spin down, and the same thing here. Okay, and I decide here to do a spin flip. Remember, this is what we have been doing before also, spin flips and then separating them. Okay, and what I see if I do a spin flip is it creates two defects. And by defect, I mean a state which isn't a 2 in, 2 out, or 2 up, 2 down. Okay? Because if you look at this tetrahedron, now that I've split the spin, it has 3 spins up and 1 down, and this one also. Okay? And so because it has created 2 defects, I can think of each one of the tetrahedra as a spin half, because a spin flip is a spin 1. And so if I think about these individual tetrahedra, and if I were able to take them, to separate them at an infinite distance, then they would each carry spin 1/2. And so this is exactly this notion of fractionalization, which in a quantum spin liquid you can actually infinitely far away separate these two tetrahedra, and they're only going to be related by a gauge field. So let me show you this thing, okay? Remember the picture I showed you for the spin-ons in 1D, so you were able to create, move 2 domains, okay? So here, but that didn't require entanglement. So here, because there's this very large degeneracy, there's a similar picture, but there's no dynamics here, okay? Because once you've picked a state, each state is static. Okay, because there is no dynamics that takes you from one to the other. But thermally, you might obtain this kind of thing. So here, let me look at a spin flip. Okay, so I had this guy. I flip it. I create those 2 defects. But now I could flip this spin again. Okay, end up with this configuration. And now I've fixed the defect in the middle, which has 2 up, 2 down. And the 2 defects have gone away from one another. Okay. So what the addition of the quantum mechanical term, so the transverse term, does for you is instead of being able to do this statically, it really creates a superposition of all these guys. Okay, and what happens is that this quantum the transverse term creates a resonance between the different classical spin-ice configurations. Okay, so if you do perturbation theory in this in J plus minus small over JZZ, you get a resonance term where which connects you in a Paracler lattice, you have these hexagons, so which connects you the blue, red, blue, red, blue, red with a red, blue, red, blue, red, blue. Okay, and this is done dynamically. So if you add the quantum, add the quantum perturbations, so the transverse term, you end up with a single ground state instead of the massively degenerate manifold. You have a single ground state, which is essentially the sum of all the 2 up, 2 down possible configurations on your lattice. Okay, so here is what I've drawn, if I haven't made any mistakes, is each of these tetrahedra has 2 blue and 2 red spins. But there are extensively many of them, okay? And the quantum spin liquid is a given superposition of all of them. And if I try to loop back to what I was telling you about non-locality, is that if you look at one given spin, okay, if I look at this one, in this term in the superposition, it's actually hard to see. It looks good here, but the colors are not great there. But this one is blue, and this one is red, and this one is blue, and this one is red. Okay, so if you were to, just measure this guy using the original spin variables, so the local variables, it would be completely hopeless to describe the state because the expectation value we would get on each of them is 0 for each spin. So it's not a good description. So the only real good description of this is actually a non-local one. And in fact, it corresponds to quantum electrodynamics, and perhaps I'll show this next time. What I just want to show here is that theoretically you might ask, how do we describe this? So the way we describe it is, as I mentioned before, we do a rewriting of the spins, and with the constraints I showed before, this is an exact rewriting. Here we create two particles, one at R and one at R prime, when we flip a spin. So S plus corresponds to flipping a spin, right? And we create two charges, okay, which are described here. And so we cooked up this thing, so I was mentioning that this parton choice, the way you decompose your spin is up to you, and you could mix however much you wanted. But if you want to get the right result, the physical result, what is given to you by nature, you need some hint. And the advantage of quantum spin ice is you have a very good hint from the classical version. Okay, so this is how this decomposition is justified, and you end up with real full-fledged quantum electrodynamics and with real deconfinement, because the defects can be moved around thanks to this transverse term. And I'm just showing this here, but since the system includes this thing every so often, well, the system, all the different possible two-in, two-out states will be entangled by acting with this guy. And so you'd see the defect every time you apply, which gets your two defects to be deconfined, and then this is the famous deconfinement of quantum spin liquids. I'm out of time, but I'll go back to this tomorrow and describe a little bit more mathematically what the difference is between the spin mean field theory and an actual mean field theory you can do on these partons and obtain the phase diagram. Thanks.
All right, I'll just start, sorry. And the two pictures before where you had the tetrahedra, I was just wondering, I understand that by flipping one spin you create these two pairs of tetrahedra that are now energetically non-favorable, but why does one have charge Q plus one, the other minus one, if the spin configurations are exactly the same? Yeah,
it's a good question. It's just that in the very beginning of showing this model, I showed that it should really be 2 in and 2 out, and not 2 out and 2 in. And so if you really think about if I were to draw this the proper way, but I thought it would be confusing. So this is all spins out on this tetrahedron, but this actually corresponds to an in spin for the next tetrahedron. Okay. And so there's a proper way to define this, which has one charge Q and one charge minus Q. Okay, so it's the orientation essentially from the. Well, it's just that because they share a site, a spin out for this tetrahedron corresponds to a spin in for the other. So the sign of the charge is flipped. So it's all consistent. Okay, thanks.
Yeah, I have a question about the emergence of the gauge fields. So in when he argues that we have introduced the Lagrange parameter to enforce the...
We have to agree.
And in Ven's book about quantum spin liquids, we have the Lagrange parameter and then enforce the constraint on average. And then if we promote it to be dynamical, then we exactly enforce the constraint, and then we have the gauge field, and this is where it comes from. And in your view, you write that you couple the patterns to the gauge field to have the gauge symmetry present again, and then you introduce all terms that are possible by gauge symmetry. So there's kind of two ways of how to bring this in, and
yeah, so so this is just one way to kind of, so Wen's book, I believe in most of the book, described this with abricosal fermions. Yeah. And there are all sorts of subtleties about how you take it's actually you end up with a projective symmetry group, and there's all sorts of choices you can make. But what I mean to say here, and I think it will become very clear in this representation here because you're familiar with the U1 gauge field from electrodynamics, is that so you could introduce a Lagrange multiplier, and then do e to the I, this sum minus 1, and this is this constraint. So this term actually commutes with the Hamiltonian, and so you end up with this gauge field. But I don't think there is anything fundamentally different from Wen's book.
But if you do this, just do away with the Lagrange multiplier and all that, then we don't have the terms that are just gauge field, right? We don't introduce these. We just have the coupling of pattern to gauge field, but we don't have
the matter field.
Gauge field terms. And
well, I'm not entirely sure I understand. But
for example, in the Z2 pattern,
yes.
there you also introduce terms of the toric code directly into the Hamiltonian.
Mm-hmm.
But if we do Wen's approach, we wouldn't get these toric code terms directly in Hamiltonian.
Yes. Yes. So there are all sorts of terms that you even in this approach. So there are other terms that you could think about including that would not come out of the rewriting of the spins in terms of these constraints, and so long as they're allowed by symmetry, you could add them by hand. So long as you consider that they're allowed and they won't disturb your phase, you could add them by hand. But here the procedure that I'm undertaking is actually to start from a spin model and then derive the terms you can get.
Okay.
Maybe we can talk about this. I'm just not entirely sure I understand the question.
Thank you for the great talk. So you already partially answered my question, actually, but my question is, so when you make this spin decomposition, so you have those local constraints, and I can see how you can get like a Gauss law out of this, but how do you get like a full electromagnetism out of that? How do you know that the full set of Maxwell equation is obeyed?
So what you get, there's a perturbation theory formalism where if you expand in what will be the gauge flux, so which corresponds to this so which corresponds basically to taking the lattice curl of this around a hexagon or around a plaquette. And if you do an expansion in this small a, so in small the b that will emerge from perturbation theory, you actually get a Hamiltonian which takes the form of e squared plus b squared. Okay, and so that's you have the same degrees of freedom. That's the Hamiltonian of electrodynamics without matter. And if you want to treat so gap defects, so that will only give you the photon mode eventually, because that's has no matter, so it only has the low energy modes. If you want to get the gapped modes, that's when you need to introduce these guys, and that's the natural procedure to introduce matter from from this U1 gauge, pure U1 gauge theory.
Okay, thank you.
Welcome.
And you could, in principle, have magnetic charges as well, right?
That's right. So, but so we don't. So there is no nice classical picture of the magnetic charges. So we work in that sector, but there is a duality between the two. But indeed, it's a good point. So we don't treat them explicitly, but they are there. So it's classical electrodynamics plus it's quantum electrodynamics, including magnetic charges.
So in the case of quantum spin ice, do you expect like area law for the entanglement entropy, or?
Yeah, so this is a good question. So I know there's some works by Sentil, for example. So here it's actually a gapless spin liquid. So when things are gapless, it's more complicated. So usually, in fact, there are logarithmic corrections. So it could be an area law with logarithmic corrections. I'm not sure the problem was in fact entirely solved, but I'd have to go back and see. But there's been works on this.
Okay,
Yeah.
thanks.
Uh-huh.